So you remember in the first vectors pack, we looked at one way of multiplying vectors together, which is the dot product or the scalar product, where you just multiply across the rows and add them all up, and you get a number at the end. Yes, scalar. There's another way of multiplying vectors together, which is called the cross product. Now, the cross product isn't technically on the Core Pure 1 specification. It's on one of the further modules, but it's so useful that I'm going to keep it. I tried to teach it. The first year I taught this, I tried to do it without the cross product, and it was a car crash. So I'm going to teach this. The good news about the cross product is that there is a formula for it on the formula sheet. So you've got your formula sheet. There is a formula for the cross product or the vector product here. So use the cross instead of a dot. There's a couple of ways of working it out. Ultimately, with the cross products, you will get a vector out. That's why it's called the vector product at the end. So there's a couple of ways of doing it. The way that I prefer is to use this formula at the end here, this A2B3 minus A3B2, whatever. It comes from doing the determinant of a 3x3 matrix with I, J, and K along the top row and your two vectors along the other two rows, which you can do if you want. But I think it's just easy to just sub the numbers into this. Okay. So I'm actually going to slip. This is the bit, this is what's in your formula book, so that's what we're going to use. What the cross product does is it takes two vectors, so there's A and this B here in this diagram here, and the resulting vector that you get from doing the cross product will be perpendicular to both of those. Okay, and the reason it's useful is for finding normal vectors to planes, because you can stick in two vectors that are in the plane and get a normal vector out. Let's practice using this. So in this example here, we're asked to find a vector perpendicular to these two things. So we're going to use the cross products to do that. Note that in the textbook, they'll do a long convoluted way of doing it, which you don't need to do, just do the cross product. So in this case, your A1, your A2, your A3, your 3, 1, and minus 2. Your B1, 2, and 3, minus 3, 1, and minus 1 from B. Okay. So I'm going to do A crossed with B, and then just substitute my numbers in. So A2 is 1, B3 is minus 1, minus A3 is minus 2, and B2 is 1. Then for the middle row, I get A3, so minus 2 times B1, which is minus 3, minus A1 is 3 times B3 is minus 1. And then A1 is 3, B2 is 1, minus A2 is 1, and B1 is minus 3. Just stick all those numbers in, work this out, so I get minus 1 plus 2 gives me 1. I've got 6 plus 3, so I get 9. And I've got 3 plus 3, so I've got 6. So this vector 1, 9, 6 is perpendicular to both these vectors A and B. Have a go at the question for you. There's a couple that I need to do. All right, here's what you should have got for these. So you should get 3, 2, 14, and 3, 4, minus 12. You can give me column vector notation. It's better. And for this one, this is just demonstrating the point that it does matter which way around you do the cross product. So if you do A cross with B, you should get 10 minus 8 minus 6. If you do B cross with A, you should get that, but with the opposite signs, and then the minus changes it all back. So they've used the determinant method. I prefer just subbing it into the formula. It's entirely. Your calculator will do the cross product for you. So let's have a look at this. So on your normal run matrix mode, it's similar to kind of all the vector, all the matrix stuff. So like putting in vectors in one place and doing all the calculations with it's in another place. So if you go on map vector, you can put in some 3x1 vectors. So for this one, if I put in 2, 1, 2, and I'm going to put a comma and put another one in. So I'm going to put 0, 3, so -3. But I don't think if you put a timestamp between them, it'll do it. And then if you press Option and map vector, is where your matrices stuff is. But if you press F6 times, here you come up with all your vector stuff. So it'll do the dot product. There's dot. It'll do the cross product as well. There's cross. They could put cross two vectors with a comma in between them. It will do that for you. Yeah. I think this vector stuff doesn't work in normal exam mode. So 7 cos and 80 on, you can't do this, but if you use UK exam mode, so if you press 1 and comma and 80 on, it does work. There's other things on here, so there's like dot product, you can get it to do angles between things, you can get it to do unit vectors. Most of the time it's faster to do it by hand, so I don't tend to do this, but you can use it as a check. Next example's asked us for a vector of unit magnitude perpendicular to both of these. So we're going to just find a vector first and then turn it into a unit vector by dividing by the magnitude. I'm going to do the cross product of these two things here. So H cross product formula, so you can sub it into those, do any calculator if you want. So we've got A2 times B3, so that's 20 minus A3 times B1, so minus 2 is 22. Then I've got A3 B1, so that's 6 minus A1 B3, so that's 5.1. And I've got A1 B2, so that's 1 times -1, so -1, -12, minus. This is a unit vector because it doesn't have length 1. So if I work out the magnitude of this, I'm going to call it n. Magnitude of n, 22 squared plus 1 squared plus 13 squared. Square rooted. 22 squared. So the unit vector we denote with a little hat and hat here. It's just the same vector but divided by root 654. I'm suspicious that I've done this wrong.
That B on the side.
Where?
On the left, in modulus.
Let's check this on the calculator. So but cross. We go back to map vector, and 3x1. 2. Another one. 3 minus 1. 5. I did do it right. And you can get it to do unit vectors of those as well. 1 minus 13. We've got option map vector. And I can do unit vector. Lovely. But you can check 22 over root 654. Here's the top one, you could check all the rest of it. So why this cross product is useful is for working out equations of planes, specifically for working out the scalar product from the plane. So r dot n equals a dot n. If you're given 3 points in the plane or 2 vectors in the plane, you can use this to come up with a normal vector. You can use this to convert from parametric form into your normal form, into your scalar product form, and then into Cartesian form as well. Okay. So here we've got an equation of a plane. We've got a point that it goes through. And we've got two direction vectors here. So we can use this information to convert this into dot product form. So r dot n equals a dot n. We need a point that it goes through, so we can just use this point, and we need a normal vector to this plane. So we're going to get a normal vector by doing the cross product of these two vectors. Okay. So take these and substitute them into the formula. So I get -1, -6, -10. -1, -9, I get -3, -2, -5, and I get -1. Okay, so you do the cross product of those two. I've done that in my head, but you substitute it into the formula. You get that. You could use that as your normal vector. Or you can use any multiple of this. So actually, I'm going to divide this by -5 and use 2, 1, -1. Or you divide it through by 5 and use -2, -1. That's fine. You can use any multiple of the normal vector because all of those are perfectly good. Normal form is r dot n equals a dot n. So we've got enough information to write that down now. So r dot 2, 1, -1 equals the point that it goes through. So 2, -3, 7 dotted with 2, 1, -1. And I can work out that right hand side, so that's just a constant. So I get 2 times 2 is 4, -3 times 1, and 7 times -1. Add those up, gives you -6. Okay, so you get r dotted with 2, 1, -1 equals -6. Converting this into Cartesian form, put in x, y, z instead of your r. And then do the dot product of that. So 2x plus y minus z equals -6, or I'm going to bring that 6 across and put +6 equals 0. Either's fine. Okay.
Why would you actually want to let?
You can use the cross product as well to get the equation of a plane containing 3 points. So I'm going to get the product form first and then convert it into Cartesian form. Any 3 points in 3D space, you will be able to find an equation of a plane passing through them. Then. So what I need to do first, I need to come up with 2 direction vectors between these 3 points. So you can use any pairs of these. Let's give them some names. Let's call them A, B, and C. So AB is 1, -1, 0, -1, 1, 1. So second one minus the first one. So I get 0, -2, -1. I'm going to use AC, but you could equally use BC as well. Get -2, -1, 1. Or you could do them the other way around. You could use BA and BC. CA. So these now are 2 direction vectors in our plane. So what we had, here's a diagram. This may or may not help. I've got 3 points A, B, and C. And what I've done is I found the vector A to B, and I found the vector A to C. From these, we're going to find a normal vector to this plane, which is perpendicular to both of those direction vectors. So we're going to use the cross product to find that normal vector. So if I do AB crossed with AC, 0, -2, -1, crossed with -2, -1, 1. This will give us a normal vector to the plane. Sub these into the cross product formula. So 3, 2, -4. That's the normal vector to the. We've now got normal vector plane, and we can pick one of the points that it goes through. Any of them is fine. I'm just going to use A. To use 1, 1, 1, and I'm going to do dot product form first. Scalar product form. So r dot 1, 1, 1 equals. So not 1, 1. R dot our normal vector, which we found was -3, 2, -4, equals 1, 1, 1 dotted with -3, 2, -4. Work out the right hand side. So -3 plus 2 plus -4 gives you -5. And then for the Cartesian form, sticking x, y, z instead of r. So you get -3x plus 2y minus 4z. Bring the 5 across. And that equals 0.